I'd like to thank the organizers for the invitation, and I also apologize if you have heard this talk before. Actually, I gave this talk a few times already. So the problem we are going to discuss is gravity water wave equation. So we assume that so basically you look at the situation in the ocean, and you assume that the air density is 0, so it's pretend it's vacuum, and the gravity is a constant. Okay, and we assume that the fluid is inviscid, incompressible, and irrotational, and we also assume the surface tension 0. So if this is omega t is a fluid domain, so it changes with time, then the left hand v is velocity, so the left hand side will be the acceleration. Okay, and we assume the density is 1. So density times acceleration is a fourth term, right? P is the pressure, and G is 0 minus G is the gravity. Okay, and incompressible, irrotational, and surface tension 0, and it's vacuum above, so the pressure is 0 on the interface. And also that the last assumption is that fluid particle on the boundary remain on the boundary for all time. Okay, on the interface, remain on the interface for all time. Okay, and it's well known that this problem is subject to, there is an important condition, which is a Taylor sign condition, governs the stability of this problem. So basically, the Taylor sign condition says that if the lighter fluid is above the heavy fluid, then it's stable. If the heavy is above lighter, it's unstable. So that's exactly what it means. Okay, and that was formulated by J. Taylor in 1949. And the strong Taylor sign condition stipulates that you also have a positive low bound. That's really just for mathematical convenience. Okay, okay, so there, of course, a lot of work on water waves, but here I just give a history on local well posedness in solvable space. So the first work was given by Nalimov for small data in 2 dimensions. Okay, so if the data is small enough, you can solve the equation for a short period of time. Okay, now so in this work, we show that actually that the Taylor sign condition always hold. So even if the wave overturns, so in other words, the heavier fluid is above the lighter fluid, but overturns not completely over, it's just like overturn, it still hold. Okay, and then we can show that for arbitrary data in solvable space, and the problem is well posed in both 2 and 3 dimensions. Okay, and this is solvability for a short time. Okay, and this lower bound holds for interface which has a little bit smoothness. So if we do not assume the smoothness, we can show negative dPdm is greater than equal to 0. Okay, so the smoothness is required for the lower bound. And this work has been extended in many directions. For example, you can add a surface tension, and it has a stabilizing effect, and you can add vorticity, but vorticity come up like a low order term. So if you want to only solve equation for a short time, it's okay. Okay, and you can also add a bottom, but as long as the bottom does not interact with the interface, that's also fine. So in all these situations, in fact, the Taylor sign condition do not hold automatically. Okay, and then you have to assume it. So once you assume the Taylor sign condition holds, then you can solve the equation for a short time. Okay. And then by now, there's also a lot of work on global behavior. Okay, so we show that about this like more than 10 years ago now, that for 2D water wave, for data of size epsilon, you can solve for time e to the 1/epsilon, and for 3D, you can solve for all time. Okay, and German Masmoudi Shatar gave a different proof for 3D, and the almost global well posedness with the almost global existence result was improved by Ionescu, Pasateri, Al-Azhar law, and just by further performing the modified scattering. Okay, and they got global existence. And so in all these earlier work so it's a crucial assumption is that the data is smooth, sufficiently smooth. So there's many orders of derivative are small, okay? And also the data decays fast enough at infinity. So sufficiently many the fast decay, and later on that Hunter, Ifrit, Tataru, and some collaborators. So they lowered the regularity threshold, and there are also actually a lot more work after that. Also try to relax the decay assumption at infinity and see like less decay but shorter time existence, like how playing with the decay rate and the existing time. But in all of these work, they're crucially there are two new ideas. Basically, it says that the reason we can do it is because after a normal form change, the water wave equation has no quadratic. So, and this is really due to the mechanism that the infinite depths to the water wave equation has no three waves interaction. Okay, and crucial for these global, almost global or long time exists a result is also you use dispersive decay property. Okay, otherwise, and the data has to be sufficiently localized. Of course, always there's a certain decay mechanism built in at infinity. But of course, if you just deal with periodic data, then we can solve only for time epsilon to the -2 if data is of size epsilon, okay, because the quadratic nonlinear term can be removed. Okay, so now the natural question is, well, can we just further remove the cubic nonlinearity? Okay, so this question has been studied actually since long time ago by Zakharov and Dyachenko. Okay, so that Zakharov found that the water wave equation can be formulated as a Hamiltonian system, and then they studied the interaction of 3 and 4 wave interactions, and they find there's no 3 wave interactions, and all 4 wave interaction coefficients vanish on the non-trivial resonant manifold. Okay, so I'm going to explain this in a minute. And then, but these calculations are formal. And in order to use this formal calculation to say that for data of size epsilon, you can have existence of solution for time epsilon to -3, because right, so you have to do some mapping properties like boundedness, and directly you cannot do that. And Craig Woolfolk and Craig Sulan were studied mapping properties, but it was like just very recently by Berti, Fiora, and Fusateri, and they can show rigorously that for periodic data of size epsilon, their existence time of the wave is epsilon to the -3. Okay, so in other words, even though they're so now what is really discovered by this Dyachenko and Zakharov? So they find there's no 3 wave resonant interactions, and then after the Birkhoff normal form procedure and doing a power expansion, there's no H3, right? So there's H4. So this is like, and then they find by studying this, there are 2 types of 4 wave resonant interactions. There are trivial ones, and there are also Benjamin Fair resonances. And now they find that the coefficient of H4 vanish on the Benjamin Fair resonances, but the trivial ones, there's no cancellation. So what it means that, say, if you really just do a PD type of reduction, say you just say, let me just find a new unknown, right? We call it V equal to U plus a bilinear term plus a cubic term. And you find that if you use this reduction, you will have a small divisor on the trivial resonances, okay? And this cannot be done. But if you use Birkhoff normal form method, it works well with a trivial resonance. So that's exactly what has been done by Berti, Fiora, and Fusateri. So they use a series of reductions based on solving polar differential equations, polar differential flows. So what they find is, so what they eventually got is some non-symplectic, but they're also Birkhoff normal form reduction is also non-explicit, okay, because they're solving polar differential flows, okay. And then they eventually say that, well, by some uniqueness argument, they say that, well, okay, so our result is the same. There's no Benjamin Fair resonances, and then we can prove for data of size epsilon, the solution exists for time epsilon -3. Okay, but so their method won't work for the whole line case because you also have to deal with near resonances. Okay, because it's okay. So in all,
Yeah,
Go ahead.
is the last one, are they in the periodic domain or are you always talking about R2?
which one? Last one. These all these work are periodic.
Oh, they're all periodic.
Yeah, they are all periodic. There's no
dispersion.
Yeah, no dispersion. Okay, no, also not whole line. So you use a Fourier series, not Fourier transform. Yes.
Could you remind us what these Benjamin resonances are?
Sorry, I didn't do the calculation. I cannot remind you this. Okay. This is I think that you know they have a very good paper. I can.
Is it like some special solution?
Yeah. So there's some some algebraic equation that's equal to 0, right? So these are the resonances.
Okay.
It's just in the Fourier modes, right?
Yeah, the Fourier modes. Yeah. So you calculate the Fourier modes, right? You know I think Javier, you did, right? So there yesterday, you write down the equation, and then you find that there's non-trivial solutions.
Okay.
So it's an algebraic thing. Okay, so all these computations are based on the Fourier space, right? Using tools, okay, from dynamical system tools. So now the question we want to ask is, well, because the equation, Euler equation is written explicitly in the physical space. What does this really mean, right? So what these reductions, which is really actually not very explicit, how does this manifest explicitly in the physical space, right? So there are several motivations of doing this. So of course, first is really just mathematical curiosity, right? So maybe there's something simple in the Fourier space, the physical space going on, right? So if you look at in the Fourier space, it's complicated, but if you look at the physical space, maybe this is something very simple. And also that, of course, this is afterthoughts. And also like, so that if you do things explicitly, it will tell you exactly what needs to be small, right? So if you, so it's like so whether the steepness of the wave need to be small, right? Because in all these earlier work, there's a lot of smallness assumptions. Many derivatives are small. So do you really need so many orders of derivative to be small, right? And below and above scaling. So maybe certain scale invariant quantity small is suffice to get a global existence, a long time existence result. Okay. And also that many of the fluid equations share same structure, right? Similar structures. For example, the one we are looking at, we ignore surface tension, we ignore the vorticity, we ignore the bottom. But if you put them back, what do you get? Well, you don't want to repeat the same calculation. So if you understand this equation explicitly, maybe you can also get some insight on some different problems, okay? Related problems. For example, this calculation are all exclusively in 2D. Can you do it in 3D? Okay. And actually the answer to this is actually yes, we do find there's a few problems that this will shed light on. Okay, this calculation will shed light on. And some of them do have quartic integrability. Okay, so now let me go back to how do we solve the water wave equation. So because we assume this is a divergence and the curl equal to 0, and in 2D, this naturally the velocity field is anti-holomorphic. So a common tool used is to use complex analysis, okay? And also because the particle, because this is a free boundary problem, and you want to just study the equation on the boundary, and because for potential flow, Laplace V equals 0, once you know what happens for the velocity on the interface, you can recover all the information inside. Okay, so now this is I see. Okay, so this is the interface equation, right? So okay, So we have this fluid domain. Okay. So this is fluid domain, and z equals to z alpha t is the interface equation in Lagrangian coordinates. Okay. And we just identified the point with a complex number. Okay, and now if you take the time derivative, you get velocity. Is the material derivative to t, you get velocity. To material derivative to t, you get acceleration. Okay, and the gravity is minus I, and because the pressure equal to 0 on the boundary, so gradient p, it points exactly in the normal direction. So if you use a decomposition between in the tangential normal direction, only normal direction survive, and it's our notation just to write IA z alpha, because z alpha is a tangent vector. Okay, z alpha is tangent, and I z alpha is normal vector. Okay, so you just A is a real quantity, and A exactly equal to that. Okay, okay. So now the first equation. So acceleration is on the interface. Acceleration is just dtt, right? And the gravity is just negative I, so move to the right-hand side, becomes positive I, and negative gradient P is IA z alpha. And divergence curl equals 0 means that velocity V bar is holomorphic. So we use Cauchy integral formula on the boundary. ZT bar is the Hilbert transform of the CT bar. Okay, so now this Hilbert transform certainly look complicated because a known function is in the denominator. Okay. Okay. So therefore, we use Riemann mapping. Okay, so Riemann mapping will induce a simpler Hilbert transform. Okay, now the Riemann mapping. So this Riemann mapping is going from the lower half plane. Okay, this is P minus. So this is from lower half plane to the fluid interface. Okay, so now of course we also know that if we call this variable alpha prime, and this Riemann mapping takes boundary to the boundary, right? So z alpha prime t will be the interface equation at time t, but in the Riemann mapping variable alpha prime. Okay, so this is the interface equation, and there is a change of coordinates between the Riemann mapping and the Lagrangian, right? So alpha prime is Riemann mapping, alpha is Lagrangian, and there's a change of coordinates given by this relation, and this b is coming from some. If you do chain rule, this quantity b will come up. Okay, so capital ZT is our notation just to say this is material derivative. dt is a material derivative, and you take two material derivative, you get acceleration. Okay, and so now the same equation we can write in the Riemann mapping coordinates. Okay, so Riemann again, this is acceleration. That's the negative gravity, and the right hand side is IA z alpha, but z alpha points in the same direction as 1 over z alpha bar. Okay, so A1 this is just a notation, but these all have been calculated like in this early paper 25 years ago, and velocity being a holomorphic now just translate to I minus the Hilbert transform equal to 0, right? And also 1 over z alpha is corresponding to the boundary value of the Riemann mapping. And also this Riemann, which is holomorphic, so I minus h of this also equal to 0. And we computed 25 years ago that this quantity A1 is 1 minus the imaginary part of this. And you just do symmetrization, and you find this second quantity is always non-negative. So this A1 is always greater than or equal to 1. And this B, this coming from this change of coordinates, is also a basis formula. Okay, so basically this equation is easier to study in the sense that now the unknown is not in the denominator anymore, right? The Hilbert transform just as simple as that. And of course, ZT is a velocity, 1 over z alpha determine the fluid domain. So we have all the information there, right? So when you know the velocity, and this is the formula that allows us to show negative dpdn as always non-negative, okay? Because it's greater than or equal to 1, right? So because this is a positive quantity, this is non-negative, this is non-negative, A1 is greater than or equal to 1. So negative dpdn is greater than 1. So even if the wave overturned, that's true. Okay, but still, this is a nonlinear equation, so we don't know how to solve it directly. And then, so we take, it turns out that by taking one material derivative, we get a quasi-linear equation. Okay. So if it takes a material derivative to this equation, let me see, to this equation, right? So you take just one material derivative, you get ztt equal to IA zt alpha plus IA tz alpha. Okay, so now you put a bar on it. It turns out these two terms are of higher order, and this is lower order. Okay, just by doing some calculation. Okay, and so this is a typical water wave operator, right? So in Riemann mapping coordinates, this becomes material derivative square, and this is just a simple change of coordinates and looks like this. And the right-hand side is a lower order term. You just use the relation that's the holomorphicity, because the left-hand side CT bar is holomorphic, and the right-hand side points only in the normal direction bar, right? So there's a relation involved, and you can find the formula for this. And this is a quadratic, and this is lower order. Okay, so typical equation of the water wave always look like this. This water wave operator acting on it equal to quadratic lower order terms. Okay. Okay, so now how do we, so now in this work about 23 years ago, 13 years ago, okay, 12 years ago, and we find that actually just by looking at certain simple transformation, the equation will have no quadratic term. Okay, so if phi is a velocity potential, and if you look at the trace of the velocity potential on the interface, and we find that, say, instead of always take holomorphic quantities in the fluid domain, you look at holomorphic quantities. So this is a projection of the velocity potential onto the space of holomorphic function in the air region. Okay, so it's I minus h. H is a Hilbert transform. Okay, so, and you also take the projection of the z minus z bar as a height, of the height of the interface into the space of holomorphic function in the air region. Then this equation becomes like, the same water wave operator, right? Acting on these quantities just equal to some cubic terms. The quadratic nonlinear term just completely removed. And now, because this quantity A still contains, this left-hand side still contains quadratic terms because A is nonlinear. But by a change of coordinates given by this, okay, so this is twice of real part of the interface minus this is a change of coordinates from Riemann from Lagrangian to Riemann coordinates, and this change of coordinates, then this will remove completely the quadratic nonlinearities on the left-hand side. Okay, so you get this simple equation. This looks like linear, but it's not linear because this is a complex value equation. Okay, this lambda is complex value. So this type of linear looking operator acting on this quantity is cubic, and this is cubic. Okay, so now we can just use an actual energy method, right? So we just look at the basic energy functional for this type of equation is given by this. Okay, now if you just look at this energy functional, and then you apply to, so we can also take arbitrary many derivative of this quantity lambda, and also for this pi, okay? And because the equation has no quadratic nonlinear term, by plugging this into the energy function, you will naturally get this equal to quartic, okay? And now, so the precise proof involves applying vector fields. So if we only work on periodic data, then we will have existence for time epsilon minus 2. And this is purely due to this energy functional, the energy identity. So now if we just also further use the method of vector fields, okay, because it has a built-in decay, right? And you use vector fields acting on lambda, and you also get something quartic. And then this gives us some dispersive decay rate, and you can yield almost global well-posed results. Okay, so now quartic inequality or quartic equality of this form also plays crucial roles in the work of Ionescu Pisateri, Alazar Delors, and Hunter, Ephraim Tatalu, and the many other works. Okay, so what they further do is that they discover modified scattering. Okay, perform a modified scattering, and to get to global. Okay, so as I mentioned earlier, the mechanism of all these earlier work is there's a lack of three-wave interactions. Okay, so because this is so important, a natural question is it possible to just like do something further to make it quintic, right? Just to move something quartic on the right-hand side to the left and then make it quintic. Okay. Okay, but so now the construction I'm going to describe works for both for the whole line and the periodic case. So this is just a pure algebraic one. Okay, so it's not, I'm not taking into consideration of dispersion or not. It's not analysis, it's algebra. Okay, I'm going to describe. Okay. Okay, so the starting point, of course, is here, right? But the problem is this is very messy. So if you want to discover anything quartic, on the right-hand side, whether it is the antiderivative of something quartic, it's like, so we can just perform something, a very simple calculation, right? So if a quantity take derivative equal to quartic, and you can see the derivative will hit on each component, right? Right, so you definitely, if you want to find the antiderivative, so if you want to find the antiderivative of some quartic quantities, you have to have these quantities appear symmetrically, right? Because otherwise it's not antiderivative of anything. Right, because if this certain quartic quantities equals to antiderivative or something, then you see this dt just appears symmetrically in each term. So the problem is in the previous work, we never thought about this. So everything on the right-hand side is not symmetric. Okay, so the first thing we look for is just really to see what kind of symmetric structure is on the right-hand side. So this, of course, this is like based on observations and a lot of calculation. So what the result, so what I'm going to describe is just the result. Okay, so this is after some long thinking and calculation, we find that this procedure will work. Okay, so first I'm going to use Riemann mapping variable because this allows the structure looks much more clean. Okay, because otherwise I have to worry about the denominator. And now this, this is the projection of the holomorphic function holomorphic functions in the low half plane, and this is the projection, right? This H is a Hilbert transform. And now I'm going to look at quantities in the Riemann mapping variable. So because in here, remember, this lambda is basically the projection of the velocity potential into the space of a holomorphic function in the air region. So I'm also going to do a projection also into the space of holomorphic, but this time it doesn't really matter if I put a bar, it becomes anti-holomorphic, right? So this is a velocity potential. So start with this quantity. So it turns out this equation is really work much better than the previous one. So the previous one, the water wave equation, the operator is you just simply take two material derivative and plus I A1 over C alpha square. Alpha. Okay, but what turns out work better is you take a material derivative. Every time you take a material derivative, you also take a projection into the space of holomorphic function and take a material derivative again. And plus I, so this is not A1, but just taking 1 over C alpha square. Okay, so A1 is 1 plus something, right? So it's a 1 part survives. And this Q is holomorphic, and if you look at pure gravity equation, the right-hand side is just anti-holomorphic. So in other words, if you take one more projection into the space of holomorphic functions, then you just get this cleanly just equal to 0. Okay, so this equation, you take one more projection, it's equal to 0. So it's just like there's no right-hand side at all. Okay, and then we perform a sequence of quantities. Every time you take a material derivative, after then you take a projection and the material projection. Okay, and these quantities we can calculate acting this operator acting on these quantity. This we can find that a very nice equation with which is cubic with symmetric structures. Okay, and also that instead of using the previous energy, so it doesn't natural for this equation, but it doesn't look very symmetric, right? So it has dt and has d alpha. We look at this one. So this one is very symmetric. So it's the alpha theta 2, and then material derivative projection of theta 1, and then minus this. And you find that if you take this energy function, though, the material is a derivative, time derivative becomes this one. Okay, and this is why also we look at this one, this operator, right? Because this appears naturally in the energy identity. So what is GK for theta? So now we just take this energy functional and takes time derivative, we get this one, and we find there's a recursive formula given by this. Okay, so ZT is this, and now 1 over Z alpha, if you compute, is exactly one more material derivative ZT. Okay, so it's ZTT plus some quadratic term, and this last one, the third one is ZT taking L many derivatives. Okay, so this like one derivative, two derivative, L many derivative, and this is one derivative again, and this is look like symmetric from this. Okay, so what is this quantity? This is a very symmetric form, right? It's look like this. Okay, so it's also two derivative, one derivative, and no zero derivative, one derivative, and L derivative. Okay, so this quantity is quadratic in terms. So I just want to emphasize with this difference. So this is quartic in terms of only derivative of 1 over ZT and Z alpha and ZT, right? So in other words, if we really want the right-hand side to be small, we don't really need ZT and the 1 over Z alpha small, but only their derivatives to be small. Okay, so this is the relation I just talked earlier. Okay, so now we have derivatives scattered term by around the terms, right? So you want to make sure you can move the derivatives, okay, to even out, look like this, okay. And then now we need energy identity which moves the material derivatives from factor to factor, okay. Now, as I mentioned earlier, for typical water wave quantities, the physical quantities satisfy this operator, water wave operator acting on them are quadratic. So it turns out this energy function, a correcting function, now you take time derivative equal to this plus quintic. Now you see this, if you look at the right-hand side, it has symmetry, right? So there's an extra dt here and there's an extra dt here. So in other words, you can move this dt to here by just performing a correcting term like this. Okay, so this allows you to move dt around and even it out and find the antiderivative. So what ends up we get is we do things symmetrically, and this is also material derivative symmetrically, and this is one of the correcting energy functional we have, and this is the second one, and it turns out that by subtracting these two correcting energy functionals and this one, and we get ddt of this is equal to quintic. Okay, so with all these explicit formula, we can see that this new energy functional controls only spatial derivatives of 1 over Z alpha and ZT. Okay, so in other words, wave with large steepness, right? So steepness So 1 over the alpha governs the steepness. So if this can be big, it's still, so a wave with large steepness and large velocity can still be small in this energy function. Okay, and if you take derivative to t, this is also quintic. If you examine this carefully, it's also in terms of the derivatives of these two quantities. So in other words, we don't need to control the steepness and the amplitude of the velocity to still get long time existence result. Okay, so this is a scaling law. So as I mentioned earlier, ideally we would really want to get a result which depends on with the smallness depend only on the scaling invariant norms. Okay, so this is the type of scaling the water wave equation observes. So scaling invariant norms are these. Okay, a half derivative and L2, and this governs this actually governs the steepness, and that's also scaling invariant. Okay, so now if I let LT equal to this, so the first line will be scaling invariant, and the second line is one more derivative above the scaling invariant quantity. Okay, so we cannot do scaling invariant. We also need to assume that one derivative above scaling to be small. Okay, so start with wave which is smooth enough. And then there are constants. So M0 is a universal constant, and epsilon 0 is sufficiently small, such that for all epsilon less than epsilon 0, okay, we have that if the data satisfy this quantity less than epsilon, right? So this quantity is small, scaling invariant plus one derivative above scaling small, and this quantity do not need to be small. So the steepness do not need to be small, it's just less than 1. So in other words, this inequality just says that the interface need to be a graph, okay? And E1 times E3 is also a scaling invariant quantity. I'm going to explain a little bit later. So E1, E3 is really just energy functionals, right? And this is M squared. Then the lifespan of the solution is epsilon minus 3. So this result holds both for the periodic and whole line case. So I'm not using dispersion here. Okay. And during this time, the solution is regular and this quantity remains small. So now what if I just assume smallness on scaling invariant quantities? Okay. So if I only assume this scaling invariant quantity small and also the steepness small, that the steepness is not small, but less than 1, right? And this is less than universal constant, then the lifespan just shrink by epsilon minus 1/2. Okay, so slightly less. And during this time, the solution is also regular. Okay, so everything here actually is scaling invariant, and the first one is assumed small. The second and third do not need to be small. Okay, so what is E1? So the energy function that we construct earlier, the E1 controls this quantity, these two quantities, and this is exactly 1/2 derivative below scaling, and E3 is 1/2 derivative above scaling, so the product is scaling invariant. And why do we need them? Because we actually need to control this quantity for all time. But the equation, at least straightforwardly from the equation, we do not have equation say that this quantity control can be controlled for time epsilon minus 3. So we use these two quantities to control the evolution of this, and this is just sovereignty embedding. Okay, so if I choose this C0 nice enough, I can make this very close to 1. Okay, so and this M0 is, we can show that this can be remain controlled for time of epsilon minus 3. So if this is less than 1 initially, then this is less than 1 for all the time epsilon minus 3. Okay, and this need not to be small. And this delta can be arbitrarily small. Okay, so if delta is very close to 0, then the steepness can be arbitrarily large. Okay, now why do we have the part 2 of the theorem? This is really like cheating. Okay, so because if you rescale your data, and then you take derivative, it gives you an epsilon in front of it. Okay, so in other words, so the rescaled solution then have lifespan epsilon minus 3, and then you go back to the original solution, it has my lifespan minus 5/2. So now if you start with a very smooth initial data, so you don't have to rescale your one derivative. You can like j many derivative above, right? So then you can say that your lifespan is this. So depending on the initial smoothness of the data. Okay. Okay. So the proof is once you have the energy functional, the proof, of course, you still need to figure out a few subtle estimate, but mostly routine. Okay. So you have this this J's order energy functional control this homogeneous Sobolev norms, and you take ddt because it's quintic, so it's epsilon to the fifth, and ddt of this is O epsilon 3 of this. So this implies that this quantity can be controlled for time of O epsilon minus 3, and provided this is small. Okay. Okay. Just finished. Okay.
Thank you. Any question? I have a question.
Okay.
What do people think about global existence in the periodic case?
No conjecture, I think.
No
Yeah, I don't think there's a conjecture on that, because you know the wave come back, right? So we don't know. So yeah.
Does numerics show any signs of blow up?
I'm not aware of this. I think there are many numerics also, but I think it's inconclusive.
For large data, you can have a splash singularity.
Yeah, but for small data, if you have
For large data, you have what?
In the periodic case, you can have a splash singularity for large data.
Splash.
Yeah.
But splash singularity is I won't call splash singularity a singularity, right? Because yeah.
I mean, disagree with that.
Because the reason is the following, right? So because you know in the very first work we can solve the water wave equation even if it overcomes.
Sure.
So you can just like you start with the data like that.
But the splash singularity is not about overturning, but self-intersecting.
Hmm?
But
yeah, it's not so it's okay. So it depends on so in other words, the water wave equation automatically admits solution with splash singularities, and you won't see it actually in the Riemann mapping variable. You solve it,
right.
You don't see this thing. It's even if it becomes intersect like crazy, you don't realize it's doing that. But of course, the physical problem is only valid when it's not. I mean, once it touches, the pressure changes on the interface, right? So from the pure Riemann mapping coordinate, that will not be seen. So
well, I mean, that's how we prove it.
Yeah, that's how you prove it. That's right. So that's the main idea, right? So because because it's not visible in the Riemann mapping variable, that therefore you start with something like this, and you really find a velocity field and pull it back, right? So then you go back because it's time reversible, and then you can do it. Yeah.
But I have in mind more a situation where the initial datum is still small,
Yeah.
What's a periodic solution? This is the best.
But no indication of a possible singularity. Okay.
Yeah. So it's whether you have a loss derivative. I think that's your question, right? So it's not clear. I think it's I don't know. Numericals, you are
not for small data.
Not for small data. For large, so splash singularity. Besides splash singularity, do you see loss of derivative, things like that?
I mean, people have reported corner formation. Not me.
Reported corner formation.
Yeah.
Okay.
The interface forms a corner.
From smooth.
From smooth without touching. Yes.
Which work is this?
This is the Russian group from New Mexico.
Yeah. Okay.
Okay.
Okay. So yeah, people. No, I think there are also some other computations. Okay. So there are other computations like Pego, Liu.
That's right.
Yeah.
That's right.
But did you try to repeat these computations?
No.
So
is it credible? I mean, does it?
I don't know. I didn't I spoke a little bit with Leo about this, but I don't have an opinion.
Yeah, yeah, I got some students to look at it and it becomes very wild. So it's, so of course it's just, we don't know, right? So whether.
Okay, any other questions? Nobody online? Let's thank the speaker again.